Want to see what the world will look like in another 50 years? Want to see it now? The idea of time travel has perplexed and fascinated many people for centuries. But it doesn't have to be so complicated. When people think about Einstein or relativity, the first thing that comes to their mind is probably E equals mc squared. That is, energy converting into mass and vice versa. When I think about Einstein, the first thing that comes to my mind is time travel. So come with me for a journey through time. To understand what time travel really is, we need to know the two basic principles of relativity. First, there is no such thing as absolute rest or motion. Everything is relative. Let's see how. Standing still, you're stationary with respect to the Earth which is moving around the Sun, and the Sun which is moving around the galactic core. Let's see it practically. If you're standing on the road, you see the guy on the skateboard move. But if you hop onto the skateboard, you will see everything move backwards. The second principle is that the first principle does not apply to light. That is, the speed of light is constant for all observers regardless of the state of motion. No matter how fast you're traveling, the speed of light will be the same for you as it is for someone not moving or moving faster. Coming back to what time travel really is, if I throw this ball, it moves with velocity v. Now if I'm skateboarding and then I throw this ball, the resultant velocity of the ball will be its original velocity plus the velocity with which I'm moving on the skateboard. Let's say in the case of light. I have a torch in my hand and I'm not moving. When I switch it on, it throws a beam of light. Since the speed of light is c, it travels a distance that is c multiplied by t. What if I were moving? I'm moving with velocity v, and then I throw this beam of light. For me, the light has traveled a distance equal to c times t. For this stationary person, the light should have traveled a distance v plus c times t, because I'm moving. But we know that the speed of light is constant for all observers, regardless of their state of motion. We have seen that the distance observed by me is smaller than the distance observed by the stationary person. Since the speed of light has been the same, time must have slowed down for me to accommodate the decrease in distance. Remember, if we have to agree with the constant speed of light, we will have to disagree on the idea of universal time. Hence, we can conclude that the time observed for a moving observer is less than the time observed for a stationary observer. Or in other words, you age slower as you move faster. And this phenomenon of slowing down time is called time dilation. Let the time observed by a stationary observer be Ts, and that by a moving observer be Tm. We know that Tm will be smaller than Ts, but how much is the difference? Or how much does time slow down for a moving observer? So here I am on a skateboard. I'm not moving, and I throw this beam of light. It travels a vertical path. Now I'm moving with velocity v, and then I throw this beam of light. A stationary observer, or you, will see the light has traveled a diagonal path. Since I'm moving along with the board, I will still see that the light has taken a vertical distance. The speed of light is c. The distance observed by me, the moving observer, will be c times tm. We have seen that the stationary observer will have a different observation of time. The distance travelled by light for him will be c times ts, and the distance travelled by me along with the board will be v times ts. So what we can see here is a right angle triangle, and in a right angle triangle, the base square plus the perpendicular square is equal to the hypotenuse square. So from this we have this masterpiece. This helps us to know how much time slows down for a moving observer. Let's try to understand it in terms of an event. First, when v is less than c. Well, this is the case when the moving observer travels into the future and time slows down for him. Then you might ask, why don't we travel into the future? Or why doesn't time slow down for us? We are traveling into the future. About 5 minutes ago, you weren't watching this video. It was future for you. But now, you're halfway through. This means that you have traveled into the future. Let's assume that these cars are traveling at the speed of light. Every time a car passes by, we consider it as an event. Now if I start moving at speeds closer to that of light, it will take each car longer time to get to me. And in the time one car passes by me, 3 cars would have passed by this stationary person. So while I experience one event, my friend would have experienced 3 events. And hence we can conclude that time slowed down for me. Second, when v is equal to c. Now if I were to travel at the speed of light, the time would freeze for me. I would not experience anything at all. In this case, the car will never get to me, as the distance between us will be the same. Since the car will never get to me, I will never experience this event, when v is greater than c. You might have heard that if you could travel faster than the speed of light, you will be able to travel into the past. Past is defined as a reference frame where an event hasn't happened yet. The car passes by me and someone throws water on me. If I travel faster than the car, I will travel into the past. Now you might think that I would magically appear when the car is about to pass me and prevent it. No, that cannot happen. Once the effect has happened, it cannot be reversed. But what I could do is that I could travel faster than the car and get to a place in space and time a few light seconds away where the event is yet to happen and prevent it from happening to this friend of mine, and that is traveling into the past. So these are the 3 cases of the equation. So if you end up meeting your great grandchildren, remember to thank Heinrich Lorentz and Albert Einstein for that.